Section 13.1 Vector Fields, Video 2. Sketching a vector field in R2. I've already set up example 1 on page 756, so let me briefly introduce you to it. The directions are simple. We're going to sketch the vector field. Vector function f of xy is equal to negative y times vector I plus x times vector j at the given points. And here I have a table where I've already given you 1 points. The first 4 are all just one unit in each direction from the origin. The bottom 3 are all 3 units in each direction, up, down, left, and right from the origin. The middle 4 are every combination of 2's and negative 2's. I've already drawn a coordinate plane up here with red dots, the 4 representing 1 unit away from the unit circle, 3 of them 3 units away from the origin. Don't know where I got unit circle. Oh, because these 4 points lie on the unit circle. And then we have all 4 of them representing all the combinations of 2 and negative 2 for both the x and the y coordinates. So let's calculate each vector, and as we calculate it, should we calculate them and then sketch them, or calculate them one at a time and sketch them after each one? Let's calculate them all. So our function says to create your vector, take the opposite of the y coordinate, and that'll be the component of the I, and then whatever the x coordinate is, that'll be the component of the j. So let's do the negation, the opposite of all of the y coordinates to give us the component of the I. So no I coordinate here. The I coordinate here, the I component will be -1, so negative I. No I here. The opposite of this would be positive I. The opposite of 2 is -2, so -2I. Opposite of 2 is -2, -2I. All right, markers getting a little chunky here. Let's see if I got another one. Don't see one handy. Again, we're doing the opposite of the y coordinate as the component for the I. So 2I, 2I, no i's, -3I, no i's, +3I. And then for the x coordinate becomes the j component. So x coordinate becomes 1j, no j's, -j, no j's, +2j, -2j, -2j, +2j, 3j, no j's, -3j's, no j's. Now you can calculate each vector completely and not do it like I did. Let's calculate the i's component. Let's calculate the j's component. However you want to do it, there's all the results of evaluating this vector function at these 12 points. Now, to sketch the vector field, we have to go to each point and from there sketch its vector. For example, from the point 0, 1, we need to draw the vector j, which is 1 unit in the y direction. So here's 0, 1. These numbers are 4 inches apart, so this is pretty easy. Well, they're supposed to be 4 inches apart. Okay, this one's a little too high, but oh well. Let's live in Colorado. Alright, so there's j emanating from the point 1, 0. Negative I is emanating from the point, or originating from the point 0, 1. So negative I would be here. 1 direction, 1 to the left. So there's negative I. From the point -1, 0, we would draw the vector -j. So here's -1, 0, and the vector -j. And then from the point 0, -1, we would draw the vector I. So 1 unit to the right. And although I haven't confirmed this yet, I believe that if we picked any point on the unit circle, it would be a vector parallel to the unit circle, going counterclockwise, with a length of 1. We might actually verify that conjecture in a moment. So it looks like we have some rotation action going on, like water in a whirlpool or something. Let's check out these other ones and see if the vectors confirm what we're thinking, that this vector field is representing some sort of rotation. At the point 2, 2, we need to draw the vector -2i, -2j. So here's 2, 2. We need to go -2 in the I direction, so that would be down, and 2 in the j direction. Is that correct? No, I wouldn't be down, stupid. Sorry. We need to go -2 in the I direction, which is 2 to the left, and then 2 in the j direction, which is up. So it would actually give me a vector whose terminal point is at 4 on the y-axis. So there's the vector -2i plus 2j. From the point -2, 2, so here, we would draw the vector -2i minus 2j. So -2 in the I direction, -2 in the j direction. That would put us down here at -4 on the x-axis as the terminal point. And there's our vector -2i minus 2j. Looks like we are getting this rotational thing. I'm going to predict that this one goes that way. At -2, -2, we have 2i minus 2j. So from here, we go 2 in the I direction, -2 in the j direction. Yep. Hooray for patterns. So here's the vector -2i minus 2j. And then, I know it's over there, but I forgot what it was. If this is following the same pattern, I'm going to predict it to go here. It should be 2i plus 2j. At the point 2, -2, it is 2i plus 2j. So here we go over 2, up 2. That puts us at 4 on the positive x-axis. That's the terminal point, with the initial point being back at 2, -2. So 2i plus 2j. So these vectors kind of confirm what I was thinking a moment ago, that this is invoking some sort of rotational action. And the further away you are from the center, it looks like that the velocity is faster because the vectors are longer. Oh wait, we got 3 more. Excuse me, 4 more. At the point 3, 0, we're going to go up 3. So 3, 0 is up 3, which is 12 inches in this coordinate system. So that would be up about here. So up 3 in the j direction. So there's 3j. This one should be -3i. 0, 3 is -3i, so that's good enough up there. So -3i. Keeping up, this one should be -3j. -3, 0 is -3j. And I shouldn't say it should be, I'm just saying if I'm picking up on the pattern correctly, that's what it will be, and I did. And so this last one down here should be 3i, 3 in the I direction, and it is. And this is an example of sketching a vector field in R2. As you can tell, when you do it by hand, it's a little time consuming. And your vectors that you sketch aren't always convenient integers. Sometimes they're irrational numbers or rational numbers or decimals, things that could be inconvenient to draw. But I am getting the feeling that this is a rotational vector field. And I'm going to move to another example in a moment, but in between this video and the one for the next example, or rather the next topic, I do want to go back to what I mentioned earlier when I said something about the unit circle. In my mind, what I'm suspecting is that all points on this unit circle will have a vector that is 1 in the unit direction and parallel to it. Is there any way we could try to verify that? Or at least the fact that it's going to be a unit vector, a vector of length 1. Well, we could, if we could somehow eliminate one of the parameters and then find the magnitude of the vector. Actually, let's do that. Let's. I think I can do this real quick. Let's just, and this is a tangent in more than one sense of the word. But let's suppose that we're on the unit circle, so that x squared plus y squared is equal to 1, is vector function f evaluated at xy a unit vector, meaning its magnitude is 1. Well, let's find the magnitude of f of xy. Well, the magnitude of a vector is the sum of the squares of its coordinates. So the sum of the squares of its components, excuse me. So the sum, let me say that again. The magnitude of a vector is the square root of the sum of the squares of its components. Square root of the sum of the squares of its components, in this case negative y and x. The negative cancels, so we get the square root of y squared plus x squared. And if we're on the unit circle, that radicand is equal to 1, and the square root of 1 is 1. So that was actually pretty easy to confirm, that every point on the unit circle will be a vector of magnitude 1. Now, can we confirm that it is also going to be tangent to the unit circle? We could do that, but I think I'm already pushing this envelope too far. And you could say the same thing with any circle of any radius. For example, these 4 points at 3, 3, negative 3, and negative 3 on the x and y axis all invoked vectors of magnitude 3. All the same reason. If the points lie in a circle of radius 3, then this would be x squared plus y squared equals 9. This would be 9, and the magnitude would be 3. So I think it's safe to say that for every vector in this vector field, its magnitude is equal to its distance from the center, aka the radius of the circle that would be on. Showing that each vector is tangent to said circle would require a little bit more work. But like I said, I've already pushed this envelope too far. Let's open another envelope.